All right, so for our last video of this unit, I want to think about what is a radiation and what is an extinction event. And so many of you have heard about the 6 mass extinctions. So what does that actually mean? And we're going to dive into what has been historically extinction and what happens afterwards. So first of all, some definitions. Adaptive radiation is the rapid diversification of a single lineage into an array of lineages, populations. So this is how we describe it. So there was some event that took place here, and that caused a rapid radiation. And niche is a range of habitats or resources occupied by a species or a population. So we've used that before. So we have two classic explanations of what causes an adaptive radiation. So ecological opportunities, so some resource became available. So an empty niche or an extinction has taken place and the populations have previously been wiped out. So we have competitors wiped out, or you can colonize a new region. So this is where, for instance, you would have cats introduced into Australia. So there was no cats previously in Australia. Now they're in Australia, and they are actively propagating and becoming quite prevalent, and that's having other consequences to other species. But all of that. The other possible explanation is morphological innovation. So, for instance, is a new way of doing something. And this gives us ability to exploit a resource that wasn't necessarily available before, or allows you to access it and more able to exploit it a little bit better. So this opens up new niches. So these are our two possibilities. And so when we first think about adaptive radiation, I want to think about historically what people like to think about. In high school, typically you're taught that when fish evolved to walk on land, once they walked on land, we got amphibians, reptiles, dinosaurs, then mammals. And it turns out that's not the case. So we had, your splitting events, and those splitting events took place. And so let's think about the splitting event here. And so we have, before we have if our outgroup here is amphibians, this right here, this monophyletic is going to be mammals. And this one's going to be reptiles. So which one came first, reptiles or mammals? They came about at the exact same time. And actually, if we look at in the fossil record, we get some mammals really early on. And in fact, mammals ruled the world. And they were quite large, quite complex. I have a fossil representation here. And this, you'd say, well, how big is this? This would be about the size of a small car. And so how do we know if it's a dinosaur versus a mammal? Well, it has differentiated teeth. That tells us it is a mammal. And so this evolved around 150 million years before any dinosaurs ever walked on this planet. And let's see if this works. I am one of those people who every once in a while will watch a stupid movie. And so here's some stupid movies. And this is, imagine you bring back that mammal and it decides to terrorize a department store. And it's the stupidest movie in the world. All right, so you might say, why did he just show me that? That's a mammal, so it's not a dinosaur. It is but it appeared in the fossil record really early on in evolution. So you might say, why? What happened? Why weren't mammals around, and why did dinosaurs come about? And that's because of an extinction. An extinction took place and wiped out most mammals, and then dinosaurs were able to take over. So why do mass extinction occurs? Well, mass extinctions are by definition, 60% of all species go extinct within 1 million years. So this is typically due to extreme rates of environmental change. Extinctions happen all the time. Background extinctions are just normal extinction rates. So a species will go extinct typically about one species per million over 1 million years. It happens quite often. We don't actually have a good indication of how often it happens because of the fossil record doesn't tell you it's the last animal to ever go extinct. It just says that that animal was present or not. So we know that extinctions happen. They happen all the time. But when mass extinctions happen, those are really prevalent, and it's really rapid, and most individuals go extinct. So mass extinctions act as like a species bottleneck event. Only very few individuals make it through, and those that make it through have opportunity available to them afterwards. So of the big mass extinctions, we have our Cambrian Ordovician extinction, the Devonian Silurian mass extinction, Cambrian, Devonian, Silurian, and then the Carboniferous. And then this one's the big guy. This is the Permian mass extinction. This is the one we're going to focus in on for a bit. And then this little itty bitty mass extinction right there, that was the one that wiped out the dinosaurs. And today we have a number of families. We have families, genus, phyla, and species available. This one we're looking at number of families. So there's a lot of individual species within a family. Very few have gone extinct so far in modern times. So when we think about extinctions, we like to think about something that's typically I call sexy, is asteroid impacts. So the Permian Triassic event happened 250 million years ago. Over 90% of existing species were wiped out. In fact, 99.9999999% of all individuals were wiped out. And so if we have an asteroid impact, and the reason why we think about that is because we can prevent it, right? We've all have all these movies, and Bruce Willis can come save you and all that fun stuff. But what would the killing mechanism for an asteroid impact be? So an asteroid hits the planet, causes massive shock waves, earthquakes, tsunamis, fire, death, all of that fun stuff. And then we look at that and we say, well, that's not necessarily the case here. The evidence doesn't necessarily tell us that. We don't see an asteroid impact crater for that time frame. We don't necessarily see any of that. So we have another hypothesis, and yes, this is the actual name of the hypothesis. It's called the world went to hell hypothesis. And so imagine that CO2 increases at an alarming high rate, and we get to a really high number of CO2. Anoxic conditions in the ocean and the atmosphere start taking place. There's very little oxygen availability. That causes mass death. The killing mechanism here is not suffocation. It's disruption of breeding. So instead of having 2 or 3 offspring, you have 1. So while individuals are still reproductively fit, they're just not as fit. We start seeing a lower reproduction. We have habitat fragmentation. We have disruption of that. And over time, we start seeing more and more individual extinctions. So asteroid impact, we can make a prediction. We can measure the instantaneous rate of death. We can see for an asteroid impact crater. We can look and see if we have any Schacht's quartz crystals. We can see if we have any ash layers, all of that. With the world went to hell hypothesis, we know we had high anoxia and we had CO2. But what caused that and what changed the chemistry? So of these questions, if we were to say, okay, if the PT extinction events, the Permian Triassic, were only due to an asteroid impact, what would be the rate of extinction of the 4 here? It'd be number 3. You'd have no extinction, no extinction, no extinction. Oh crap, the world was hit by an asteroid. Everything dies, comes back. There's no extinction, no extinction, no extinction. That is because if we were to think about an asteroid impact, how quickly does everything die? Does it take hours, days, minutes, years, thousands of years, millions of years? It takes place on the order of hours to days to weeks to a couple of years. Within a few years or 1,000 years, things are returning fairly back to normal. Whereas if something like here is telling us, oh, over 25, 50 million years, we just had a high extinction rate. So, oh, we're going to see an asteroid coming, asteroid coming. Oh, the asteroid hit, still maintaining. So that's not the best one. All right. So if it was an impact, what was it? It was the world went to hell hypothesis. So mass extinctions are short periods of when microbial communities take back the world. And this is kind of, this joke is this, the Empire Strikes Back to Precambrian. So Precambrian means that before animals. So the Gaian theory is that life hates life. Life wants to assassinate life, wants to take over life. Mm-hmm. Gaia hypothesis is basically the movies where life loves each other. Pandora, the all of those movies where life is facilitating other life. So if we look again at this mass extinction, we notice that every time CO2 rapidly changes, that was a rapid increase in CO2, we get a mass extinction event. Back down here, before the Permian, the world was very similar. These was dominated by mammals. And you start seeing we get this rapid acceleration of CO2 to about 3,000 ppm. What happens to all the mammals? They die out. But dinosaurs and reptiles survived just fine. Only a handful of mammals made it. And all those mammals kind of lived in the shadows until the dinosaurs were wiped out by a mass extinction by an asteroid impact. We say, well, could an extinction event take place that's caused by rapid cooling? Yes. In fact, we have some of those events. We actually think that our Ordovician extinction actually might have been right afterwards caused by a rapid cooling event. So if we look again, what about our near future? And we looked at this graph earlier, but yeah, we might see that. Now you say, okay, well, what level causes a mass extinction? Is it 400 ppm CO2? Probably not. But 2,000 or 3,000 level of ppm CO2? Yes, absolutely. We're probably in a post-glacial world. The ocean levels are quite high. Anoxia is taking place. But here's the biggest key: speed. If you increase CO2 over a long period of time, species have time to adapt. They can move. Ecological niches can open up and close. You can have this meta-population dynamics. But if you increase CO2 concentrations by huge percentages part per million in a very short period of time, now it's a mass extinction event. In this event, in the Permian extinction, we see this massive change in roughly about 3 million years. We have done what it took 1 million years to do historically. We did it in 100 years with our CO2 levels. So that's where it becomes really dangerous, and we could have a sixth mass extinction. So let's think about this. Are we in a current mass extinction today? And the probability of that is no. We know that 60% of the species have not gone extinct today. So this is not a mass extinction currently. Could we get there really easily? Yes, absolutely. And it could be a sixth grade extinction. Now, do you want to live in a world where there's a sixth mass extinction taking place? No, because chances are you're going to die. And the reason why we can say that is that if 99.99999% of all individuals die during these extinctions, then most individuals on this planet will die. Very few will survive. Very few animals will survive. Very few plants will survive. Those that do survive will have great ecological niches open up and opportunity available to them afterwards. But that's not right away. That's going to take 1 million or 2 million years to recover. So do we want a mass extinction? No. Could it happen? Absolutely. All right, so the last thing here we had back to the Permian-Triassic event is the Kump hypothesis. And so what actually kills individuals when you have rapid climate change? So imagine a world where CO2 levels are increasing rapidly. The world's getting warmer. When water gets warmer, it becomes more stagnant. You get lower circulation events taking place in your ocean. That's going to allow for bacteria to build up. Bacteria, when they build up, they release hydrogen sulfide. Hydrogen sulfide is that rotten egg smell. And when you smell that, that's a good mechanism in your body saying, this is really dangerous. It's going to kill me. H2S poisoning does kill individuals. And so when you start getting this, you just start getting rapid mass death in localized areas. We've reduced the reproductive success of an individual and a population. And now small little events that typically would not have just caused them to go extinct, go extinct. And that is what happens. It's not an instantaneous event. We get habitat fragmentation. That's causing low levels of population diversity, causing reproductive isolation and inbreeding, causing bottleneck events, diseased alleles to increase, reproductive success is being limited. And then just for fun, we have some event like a hurricane or an earthquake or some other thing that takes place. And the next thing you know, that's an extinction event. So consequences of extinctions, new niches open up, changes in the environment, reduced diversity in the short term, changes in allele frequency, which ultimately causes evolution. And but after every previous mass extinction, we had ecological opportunity and increase in diversity. So this one, we had the number of genera. So the previous one I showed you was number of families. And again, we have our different extinction events. And this one shows a little bit more, but that one's the ones that kill off the dinosaurs. So today, if we had an extinction event, it would probably look like that. And afterwards, it would grow, which ultimately for the history of life is good. But for an individual living in that time, very bad thing.